So far, in the previous videos, we've done addition, subtraction, multiplication, all standard things to do with, we're carrying over things from real numbers over to complex numbers. This video, we're going to have the first couple of things that are very specific to complex numbers. So first, we're going to see complex conjugation, and then we're also going to see the modulus of a complex number in this video. So what's going on here? So the complex conjugate of a complex number z is equal to x plus iy is going to be z bar. We put a bar over the z to denote that we're finding the conjugate of it. We keep the real part the same, and we slap a minus sign on for the imaginary part. The imaginary part becomes negative. So as an example of this, if we were to have z is equal to 3 plus 2i, z bar would equal 3 minus 2i. And so the real part stays the same, the imaginary sign part gets flipped in sign. What about this modulus here? So that's going to be, the definition of the modulus is you put absolute value bars around z to denote that you're finding the modulus, and it's defined to be the square root of x squared plus y squared. It's the square root of the real part of z squared plus the imaginary part of z squared. So as an example of that, as an example of the modulus, if our z, I guess I can keep the same example from before, 3 plus 2i, the modulus of z is the square root of 3 squared plus 2 squared. It's the square root of 9 plus 4 is 13. Okay, so that is some standard calculations to do with this. Of course, we have like the kind of trivial example. Let's say z is just I. If z is just I, the complex conjugate of I would just be negative I, and the modulus of z would be square root of 0 squared plus 1 squared is just 1. So that's what's going on here for the complex conjugate and the modulus. In a video or two, we'll see a geometric reason why we put absolute value bars around the complex number to find the modulus. There's a good geometric reason for why we do that. To kind of end this video, I want to talk about some properties here so a bunch of properties of complex conjugates and the modulus. And we'll kind of see why these two concepts, right now, these seem like distinct concepts. We see that there will be a little bit of overlap here. So the first property here basically says that if you take the conjugate of z, and then you take the conjugate of z, you get back to the original number. I'm not going to do formal proofs. You can see the notes posted to Canvas for formal proofs. I just want to illustrate each one of these properties very quickly here. So in number 1, let's just say that z is equal to 3 plus 2i. I guess that's the same one I've been using all along. Then the complex conjugate of z would be 3 minus 2i. And then the conjugate of z, take the conjugate of this, 3 plus 2i. So we can basically see why this is true. That taking the complex conjugate merely changes the sign on the imaginary part. Flip the sign twice, you're back to where you started. Second one says here that if you take two complex numbers z1 and z2 and add them together and then take the conjugate, you get the same thing as if you had just done their conjugates first and then added them together. Again, let's verify this. For z1 is equal to 2 plus 5i, and z2 is equal to 1 minus 3i. And so then z1 plus z2 is going to be, add these together, 2 plus 1 is 3, 5i minus 3i, by accident, z1 plus z2 is equal to z. I wasn't intending that, but let's just see what happens here. So the complex conjugate of the sum here is going to be 3 minus 2i. And then if we do the conjugate of z1 plus the conjugate of z2, we see that we get 2 minus 5i plus 1 minus 3i, sorry, 1 plus 3i. And see for yourself that yes, when you combine this together, you still get 3 minus 2i, which is as before, so that checks. The third property here is that the conjugate of a product is equal to the product of the conjugate. So, you know, we might be hoping that such a statement is true, and it's not guaranteed that it's going to be true, but it is true in this case. Again, see the book if you want a formal proof of it. Let's just verify it in this case. So z1 times z2, I'm still going to be taking the same z1 and z2 here. z1 times z2 gives you 17 minus I. It might be a good idea for you to verify this yourself. If you're still practicing with this, I won't show you the details there. And then if we do the conjugate of z1 times the conjugate of z2, so that would be 2 minus 5i times 1 plus 3i. Check for yourself that you get 17 plus I. So, and this is, of course, going to be equal to the conjugate of the product here. So see, you know, take the conjugate here, you get 17 plus I. So we came up with this in two different ways. We multiply them together first to get 17 minus I, and then took the conjugate of that to get 17 plus I, or we took the conjugate first of each one of them and multiply those together to get 17 plus I. So once again, if you need some practice, you may want to calculate those products there yourself to make sure you are fluent in doing the multiplication yourself. Let's see, there's three more properties I want to do, two of them on this slide. So this is the first one where you kind of see the connection between, and this is the reason we are doing these together, the connection between the complex conjugate here and the modulus. So this says that if we take a complex number and multiply it with its conjugate, we get the square of the modulus. And take a moment to appreciate just how cool this is and how surprising this is. That this number here, z, is complex. You know, we're assuming it's complex, and it's, you know, its conjugate is also going to be complex. But when we multiply them together, we get something real, and not just real, but real and non-negative. We are, you know, the modulus is, probably should have said this earlier, you know, this is to emphasize the point that this is a real number. And so it is cool here that we multiply a complex number by its conjugate, you get the square of its modulus, which is real. Using the same example as before, z is equal to 3 plus 2i. So the conjugate of z is 3 minus 2i. Let's multiply those together. 3 plus 2i times 3 minus 2i. I will do this one from scratch so you can see what's going on here. So 3 times 3 gives us 9. 2i times 3 gives us plus 6i. 3 times minus 2i is minus 6i. So you can see that the imaginary parts are going to cancel out. 2i times minus 2i is minus 4i squared. but minus 4i squared would be plus 4. Cancel, cancel. Plus 4 is equal to 13. And way back here, what was the modulus? The modulus was the square root of 13. So if we do the modulus of z squared, we get square root of 13 squared is 13. So once again, this checks out. Our fifth property here, the modulus of a product is the product of the moduli. And let's see that. Let's again use the same ones here. Z1 is equal to 2 plus 5i. And Z2 is equal to 1 minus 3i. So let's see, and we also we made the effort to multiply them together. So we've got Z1, Z2 is equal to 17 minus I. Okay, so let's figure out the moduli here. The modulus of Z1 times Z2 would be the square root of 17 squared plus minus 1 squared. And that ends up as 17 squared is 289. So 289 plus 1 is 290, square root of 290. The modulus of Z1 is going to be the square root of 2 squared plus 5 squared. And that's going to be 4 plus 25 is square root of 29. That is what we get there. And the modulus of Z2 is square root of 1 squared plus minus 3 squared. 1 plus 9 is 10. So this is square root 10. And lo and behold, this is pretty cool. This is pretty cool. The modulus of Z1 times the modulus of Z2 is square root 29 times square root 10, which does in fact give us 290. Just as we square root of 290, just as we'd want. So yes, I mean, if you want to see, once again, if you want to see a formal proof, see the book, see the notes for this. But we are just verifying here. And then one more property here says that the real, for any complex numbers, the real part and the imaginary part are both less than or equal to, in absolute value, than the modulus of the complex number. So very quickly, let's just verify that one final time with z is equal to 3 plus 2i here, that the real part of z is equal to 3, the imaginary part of z is equal to 2, and so let's just very quickly, let me pull out my calculator here. The square root of 13 is about, square root of 13 is about 3.606. And so we see here 3 is less than or equal to 3.606, 2 is less than or equal to 3.606. In these cases, both of them are strictly less than. But for example, if z were equal to, let me say, minus 3i here. So the modulus of z in this case would be the square root of 0 squared plus minus 3 squared. The square root of minus 3 squared would give us 3. And the absolute value of the imaginary part of z is going to be the absolute value of 3, which is equal to 3. So we do have equality here. It is possible to achieve equality.